Hello, everyone. Today, this is Machine Learning 201. So what we're going to do, and by we, I mean myself and Aliyah Atwi. Does everybody know Aliyah? Aliyah works for HealthShare Development and taught machine learning at MIT, unlike me, who's taught machine learning only in 2H, 2I. So I'm going to do a little bit of reminder of last time, and then we're going to go into the neural network. Basically, that's the main theme of this session. So who wants to walk me through what I taught you last time? Does anybody remember anything?
Ensemble solutions where you combine different discriminators into a combined one?
Yes, that's a good one. Yes. Ensemble methods, where you have kind of different machine learning algorithms and you combine them together, and you get a better answer even. Anybody else remember anything? Yes?
Random forest and decision trees were particularly effective.
Very good. Random forest and decision trees. And I won't remind you of that one, but that's a really excellent approach to deal with nonlinear data, which neural networks are another approach. All right, I'm going to remind you of what I went through in this beginning part. But first, I'm going to throw out the challenge that we'll solve in this hour, which is how to write a program that recognizes handwritten digits. Okay? And the difference between traditional programming, where you're sort of writing a bunch of if-then statements to figure out things, and machine learning. So who knows how to write a program that would identify handwritten digits using traditional methods? I can tell you that I have no idea how I would approach this problem. You know, this to me would be a very hard program to write. You know, looking for lines or round things, you know, how many round things are in this picture, how many lines, how many are vertical, how many are horizontal. I could just imagine spending half a year trying to write this program. Okay? We'll see machine learning will not take us half a year. It'll take us much less to write it. So that's the example. Last time we went through the flowers example, the iris flowers. This time it's handwritten digits. That'll be our data set that we use for this session. Okay, and then a reminder of the approach. With classical programming, you have your rules. You run the data through those rules, and you come up with your answer. In machine learning, you just give it lots of data. So in this case, lots of handwritten digits. You give it what each digit is in a training set, and it actually figures out the rules. And then you can apply those rules to recognize new digits. So that's the basic model. Okay, so again, I'm going to take 10 minutes and just recap last time. So the terms AI, machine learning, deep learning may sound all the same, but just to clarify the slight difference, AI is the superset. It consists of non-machine learning techniques as well, essentially like the way computers used to play chess or things like that. Machine learning, and then deep learning is a type of machine learning that Aliyah will introduce you to in a moment. Okay, and then we went through these algorithms, or much of these algorithms, last time. These are mentioned, decision tree, random forest. And the main algorithms went through are the concept of linear separation. And the concept with linear separation is, if you recall, like in the adults versus child analogy, that if you graph out your two classes, let's say, that they would be separate from each other in the mathematical space. The mathematical space, when you have two features, is a simple xy axis, that the x's are in one place, or the adults are in one place, the children are in another place, and you just find an equation for a line that separates out those 2 points. Okay? So that's the idea behind linear separation. So that's a building block you'll see of neural networks as well. And so machine learning really is figuring out this function that takes the features that you have about a particular thing, an instance, and determining its class. So the part of machine learning we're talking about is classification. So, so the two features here are like height and money in the bank, and you have to determine whether it's an adult or a child. While I'm on the board, I'll tell you about the features of this data set of handwritten digits. So each digit is codified in a 28 by 28 grid. That's how many pixels there are. And each pixel has the grayscale value of that pixel between 0 and 255. Okay? So each digit, like if I write one, I'll just write an 8. You have the pixel value of each of these. And essentially, you can imagine each digit as a table, like we like to do. And each digit is a row. It'll have 784 pixels, grayscale values, and then it'll have a label. Which digit is this? So that's the structure of the data. So funny story, I was doing this little data set in my book, and then that evening I went to the Cambridge Side Galleria. And you know, there's that beer bar as soon as you walk in on the left. It's the World of Beer or something like that. And they had a quiz night. And the very first question was, what is 28 squared? And I immediately answered 784. And the guy thought I was a genius. And I normally can't go past 12, but somehow 28 squared was on the tip of my tongue. But essentially, it's no different. So if you somehow imagine, from a linear separation point of view, imagine being in a space with 784 dimensions, in a sense. And it's a little bit hard to imagine, but the zeros are over here, the ones are over here, the twos are over here, that each of the 10 digits are in different parts of that space. And you're trying to identify what would be called a hyperplane that really separates out the 10 segments of that space. So that's linear separation. It's the same mathematically as the 2-dimension. It just has a lot more dimensions. But the math is the same. And it looks like this, as you recall. Should have it here. It looks like this. You have each of the features. So each digit will have different answers for the x's. And then you need to find the weights. That's what linear separation is. That somehow you have to find the weights, and those weights multiplied by the features and added together, essentially, you compare it to, if it's greater than 1, it's one digit. If it's less than 1, it's another digit, at least for the binary case. So how do we find the weights? Again, this is the review section of it. So it turns out you can do these handwritten digits in 29 lines of code. Like I said, that it would take me 6 months to do it in another fashion. But it's just this 29 lines of code, which we won't go through in line by line. But essentially the way it works is it randomly picks 785 weights. And then it does this a lot of times through the data set. It'll run one digit by one digit. So it'll take this first digit, and it'll guess, hey, this digit is a 6 or a 7 or something like that. It'll either get it right or wrong. And if it gets it right, it leaves everything alone. And if it gets it wrong, it adjusts the weights in the direction of being right. And you just do that a few hundred times in this outer loop. The number of iterations. And then eventually you have a series of weights that really separate out these different classes. Okay, so let's see how, and this particular one is called Logistic Regression. And let's see how it works. First of all, back on the magic of this. So I think this is amazing that 29 lines of code can basically separate out handwritten digits. But it's not just 29 lines of code. What else is it? The data. So what we have in this case is we have a data set where 60,000 digits were handwritten, and then somebody said, I wrote a 6. Or I wrote a 6. So labeled data. So some group of students spent hours kind of writing all these digits. So the magic is really in the data, plus these algorithms. But these algorithms are 50 years old. You know, it's really having nice, clean digital data, actually, that makes this thing work. But anyway, let's see if it works. So let's take a look at this database. Oh, it started training. Let's get out of that. Maybe that's why my PC was acting up. It's training this thing. Okay. All right, these are, for instance, the first, let me minimize that. These are the first examples of each of the digits. And then there's variety, of course. So this is the first 25 sevens in the data set. So even if you were to write a program, you'll suddenly remember, oh, people write 7 slightly differently. So some people cross the 7. Where's that? Some people do 3 lines, a little cap on the 7. I guess that's about it. So there's a few different ways of doing that, and that's true of many other numbers. Okay? And some people write their 7s very poorly, just like 1s, as it turns out. Okay, so we're going to solve this problem using twice. One is this logistic regression that I just went through, a simple linear separation. And then we're going to dive into deep learning and show how that may improve it. Okay, just a slight reminder on the formula to do this, because it's slightly more complicated than I've led you to believe. But you essentially have this first row, let's say, and it's put on its side in this picture. So here's an example digit. Here are the 784 features. There's one extra weight in the front, so there's 785 weights, and you're multiplying, doing the dot product, essentially, of the weights and the features. And then you get either a really positive answer, 0, or a really negative answer. And there's a squashing function, which is called the sigmoid function, that basically turns it into somewhere between 0 and 1. And what that effectively means is that the answer to this equation is the probability that this particular digit is a 7. Every digit has its own set of weights. So if you assume these are the weights for 7, this is the probability that this digit is a 7. Okay? Then you have the right answer, which is either 0 or a 1. Either it's not a 7 or it's a 7. The probability of a 7 being a 7 is 1. So essentially, you have a probability here between 0 and 1. You have the number 0 and 1. You subtract the 2, which is how wrong am I, and that drives the change to the weights. So that's essentially the formula. It's also the case that we have 10 digits. So essentially, it's like the way I described, except you do it for each of the 10. So it becomes 10 times the 785 weights, or 7,850 weights. Okay, so there's a lot of weights in this particular case. Okay, so let's see how it does. So last time I ran them all live, but this time actually the training takes about a half hour to do this. So I have recorded it. And I could post on YouTube if you guys want to watch this. But essentially, it runs through 35 times, the 60,000 images, keeps adjusting the weights, and it gets a 92% accuracy. It's pretty good. Pretty good for 29 lines of code, I think. This is why I like machine learning. I'm like, this is amazing. I would spend my whole career trying to write this program. But OK, so here's its results. T means the target, the right answer, and P means what it predicted. And you can see in this case, it got this one wrong. This is a 9, and it thought it was a 1. OK? We could have figured that out, these dumb computers. And this was a 5, and it thought it was a 6, which is quite understandable, actually. Yeah, this person should get some sleep, be a little bit more articulate with his or her writing. And the rest it's got right. So it got 23 out of 25 for the first ones. And this is the first 25 that it got wrong. Okay, so if you just pick the wrong ones. And you can see, I don't know, these are, you could get these right, you know? So this isn't quite, this is a very simple algorithm. So, but these are kind of the one, and some you could see, you know, it might get wrong. You know, God knows what that is, or that, you know. Okay, so that concludes the review of last time, which is kind of linear separation and how it does on handwritten digits. So now what I'll do is I'll turn it over to Aaliyah, and she's going to dive into deep learning and describe what that approach looks like. Okay?
Right, thanks, Don. Okay, so we're going to use linear models and build up on them all the way until we reach deep learning. So for that, I'm going to focus on this simple example. So say we're building an app, and the app is supposed to predict whether or not you're going to get accepted in your favorite university or not. And as input, we wanted to take your SAT scores and your school grades, and then do its magic and give you a prediction. So how would we go about building this app? We would probably go to last year's results, so last year's applicants, get all their data, what were their scores, what were their school grades, and what was their outcome. And then look at a scatter plot like this and try to see a pattern, right? So the pattern here is, you know, if your grades are high, you will get accepted. If they're low, you won't get accepted. And this is very easy for a human to see. The question is, how can I make the app actually do this? How can I make the app recognize this pattern? So looking at the data, luckily, in this case, you can actually draw a line to separate the examples that are accepted or rejected. So if you give the app the equation of this line, it should be able to get a new student, their SAT score and their grades, and then it would use a perceptron. So it would sum up, take a weighted sum of their SAT score and the grades, and if that sum is positive, i.e. if the point lies above the line, it will predict that, okay, this student's likely to get accepted. And if the weighted sum is negative, it will be below the line, so rejected. And this is the basic linear separator that Don walked us through last time. So it turns out that even though this looks simple, it's very similar to how the brain works. So when the neurons in your brain, they just take input signals from dendrites and then do some processing on them. And then based on that, they decide whether to fire or not through the axon. And if you want your app to be more sophisticated, so instead of saying, yes, definitely you'll get accepted or definitely you'll get rejected, maybe you want the app to output a likelihood of your acceptance or rejection instead. In that case, we can still use the linear separation. We just, instead of having a 1-0 output, after we take the weighted sum of your SAT scores and your school grades, instead of just outputting yes or no, we will enter that weighted sum in the sigmoid function that Don just talked to us about. And the sigmoid function, no matter what the input is, if it's minus 15, plus 300, whatever the input, it will squash it and produce an output that's between 0 and 1. So it can be interpreted as a probability. And so if you look here, all these points that are accepted will get a likelihood that's over 0.5, and all the points that get rejected will get less than 0.5, and then things that are on the boundary will get a likelihood of 0.5. And this is logistic regression. Now, in reality, we might not be so fortunate that we can just drop a line between our data and get it separated perfectly. In reality, maybe no matter how high your SAT score, if your school grades are low, you just won't get accepted. So in that case, a linear model will not perfectly separate this data. And I guess the question is, can we find a nonlinear model to separate the data? Now, we've seen many ways of doing this before in Don's previous session with trees and all the other stuff. But now we're interested in a specific question. Can we use linear models as basic building blocks and use them to produce a nonlinear model? And the answer is actually a yes. And we'll see how. So basically, I'm saying, if I have this linear model with this separation that's linear and this one, would I be able to do some magic, combine them, and produce a nonlinear region? So let's try to do that. So say I have two linear models that each make their own attempt at predicting whether a student will get accepted or not and what their likelihood of acceptance is. And say we focus on this one student. Model 1 says the student has a 0.7 chance of being accepted. Model 2, which is also linear, says that the student has a 0.8 chance of getting accepted. Now, say I want to combine their predictions in a way that I get this nonlinear separation here. How would I combine these predictions? I'm going to start with the basic way to combine two numbers, and that is just summing them up, right? So I'm going to sum the prediction of the first model and the second one and get a 1.5. But this is unsettling. 1.5 is not a probability, right? So how can I take a number that's 1.5 or something that's not between 0 and 1 and convert it to something between 0 and 1? What do we use? Sigmoid, right? So I'm just going to sum up the numbers, take the output, plug it in a sigmoid, and here. So I have a 0.82 probability now. Now, what if my first model is much more trustworthy than the second one? Maybe we did a better job with the first model. So I want to kind of emphasize its prediction a bit more. So instead of a linear sum, what can we do? Take a weighted sum, exactly. So I'm going to multiply the first prediction by 7, the second one by 5. Heck, I might even subtract a 6. Take just a linear combination, and then I have 2.9 as a prediction. Again, that's not a probability. And again, we use a sigmoid and get a 0.95. Now, it turns out that if we do this procedure for all the points and look at the points that have a 0.5 probability, like the uncertain ones, the boundary, that boundary will actually look like this nonlinear boundary over here. So it seems like we actually have a way to take two linear models, combine their predictions, and get a nonlinear separation as a result. And what we did here is basically we took the first perceptron and the second perceptron and got a weighted sum of their results, squashed it in a sigmoid, and that's what we actually implemented. So it's the same as stacking your perceptrons. So we use a third output perceptron to process the input of the two and produce its own prediction. And we don't have to stop at just combining two models. Yes, Ariel?
I'm curious why you decided to add a fixed weight, the -6.
Because the general equation of a line is, it has a bias term, which is just a constant. And so this is the most general way to do it.
So you were looking at the data and seeing it needs to be shifted. You just said, look, an example of that stuff.
Yes, so right now I'm assuming these models are given and that I know all the weights, but in reality, we need to train these models to fit our examples properly. And so in the training process, it might end up that the best way to fit the model is to choose, say, the number 6 to subtract here. Yeah.
That is actually one of the weights. So in the training process, it's going to train all those coefficients and that weight at the end.
So I understand computation is much better when I add and when I do linear things. If I had it in my mind to take those two graphs, which are both showing a probability across the same distribution, in my mind I probably would have multiplied. Right? That would have been my intuitive answer, would be to take the 0.7 and the 0.8 and probably multiply, and that would have been the distribution I looked for. But we don't see that very much. Is that simply because of the need for computational simplicity, and is that in fact, and we find out that when we do it a million times, it doesn't matter? Is that sort of where we're going?
Yes, so basically we want to repeat the same process multiple times. And so since so far we've been taking linear combinations, we want to continue doing that recursively to build bigger networks. If we change what we do at each step, then it won't build up very easily into bigger things. Don, do you have?
That's okay, yeah.
Yeah. Yes.
I also think in this case, since you're multiplying a bunch of probabilities, as you try to get more layers, all of your probabilities will be zero.
Well, again, normalized.
Yeah, but
Yeah, multiplication will squash numbers to zero, and yeah.
But hey, you added factors, I can add factors.
Maybe we'll invent our own network. Okay, so in the previous example, we just combined the predictions of 2 models, right? But there is nothing stopping us from combining the predictions of, say, 3 models and then getting this more nonlinear region, so this triangular separation over here. And there's nothing stopping us also from having multiple layers of linear models feeding into each other. And the more we do this, the more nonlinearities and subtleties we can catch in our data. So when we have multiple layers like that, that's, I guess, what we call a deep neural network. This would be the output layer, this would be the input layer in the beginning, and these guys are the hidden layers. Now, a question is, like so far we assumed we just know the equation of this line or all these equations that we need, all the parameters. But in reality, we want the data, the previous data, to determine these equations for us. So the question is, how do we find the right parameters so that we accurately predict the data that we have? Yes?
Is there like a problem of overfitting like into 2 layers?
Yes, sure.
Can you repeat the question? Is there an issue with overfitting if you have too many layers?
Can you repeat the question, actually?
So
Yeah,
the
yeah.
question, Shisha's
Yeah.
question was that, is there an issue of, is there a risk of overfitting if we have too many layers? Of course, if your data is really simple, you want the simplest model possible to represent that, and no simpler, right? So if you're using 1 million parameters for something that's very, simple, then there is always a risk of overfitting. So the usual things we have to watch out for in any machine learning algorithm, we still have to watch out for here. So the training, yes. Sorry.
Anytime you do successful approximations, you can always get into the wrong well, right? You're trying to get to on this side of the curve, but it turns out that you slip and you find out that you're on the other side. If you're trying to do a square root, you'll sometimes wind up with an answer that's not near where you were. I imagine that when you do this with so many of these, you can have that happen very often. Does this self-correct in general? What is the...
No, we have to.
Go ahead and repeat the question. Yeah.
I think the question is that, I believe the question is about potentially falling into local minima or something, or local optimal solutions. And so we still have all these risks that we would have with any machine learning algorithm. So in the training process, there are all these clever ways, I guess, all these clever inputs you can give to your optimizer to get it to jump over local minima. And so the same problems will still exist, and the same kind of approaches are still out there to try and circumvent that. So the question of training, again, is if I have a bunch of historical data with their answers, I'm going to try to find the best parameters for the model so that I most accurately fit the data I've seen before. And Don has already kind of talked to us about this a bit. We use stochastic gradient descent to accomplish this. So what this means is that we're going to start with a random guess for the parameters, just completely random guess. And then we're going to see how well we're doing. So if I just guess a line, how well is it actually separating my acceptances and rejections? And so we find the current prediction of this guess model, and we compare it with the ground truth that we know. So for a given student, say we know that this student definitely got accepted, but the model is predicting a 0.1 likelihood of them being accepted. Clearly, there is an issue there. Alternatively, maybe the model is predicting that with probability 1, they're getting accepted. In that case, we can just, we're fine. The model is doing well. But if there is a discrepancy, we're going to calculate the difference between the model's prediction and the ground truth. And then we're going to try to tweak the parameters to minimize this error. And the way we do this is by finding the gradient of the loss relative to these weights. So the gradient will give us the direction that is most efficient for us to tune the weights in to minimize this error. Now, forgetting all this stuff, what I want us to know here is that if we had this simple one-layer perceptron, once I have the error, I can easily use that with this update equation to tweak the parameter weights. Now the question becomes, what happens if I have multiple layers? How can we train the parameters then? So let's go back to what we know from the single layer case. So we know how to update the parameters for this last layer, right? So I can plug in the examples, get the prediction, see how far they are from the ground truth, and then use the equation from the previous slide to update the weights over here. The question is, how do I update the previous layers? So what we're going to do is we'll take the overall error of the network and try to attribute how much of it is caused by each of these nodes. So I'm going to assign blame. This guy contributed most of the error, and these two maybe contributed less. And we do this by taking this error term and propagating backwards in the network, like passing it almost as an input from the end of the network backwards. So this will give me that this hidden node contributed this much of the error, this hidden node contributed that much, and so on. And then once we have that, we're back at the single layer case. So I can forget the output, which we already took care of, and then use the equation from the previous slide to calculate the weight updates at this layer. And we can keep continuing this process. If we had more and more layers, we can just keep going recursively. Now, luckily, we don't actually, in real life, have to worry too much about the tedious implementation of this. In practice, we can just use a package.
Sure.
So Keras, TensorFlow, I don't know, PyTorch, all these things we've heard of, they take care of the nitty-gritty of backpropagation for us. So usually all we have to specify is the model architecture, how many layers we want, how many nodes in each layer we want, and then we feed all the training data, and then it does its magic and does the training for us. So now I'm going to hand it back to Don to tell us how neural networks work for the handwritten digit recognition.
Yeah. What would you guess? Let's see for sure. Yeah, 96, Jeff. That's excellent. Yeah. Oh, let me stop it too. Okay, so so this actually had 42,000 weights. So there were two hidden layers of 50 each. So you had the beginning layer, 785. You had the end, which was 10 digits. And there are two layers in the middle, which were 50 cells each, basically. So that ends up being 42,000 weights, because you have this many to get to the first layer, this many between the two hidden layers, and this many from the second hidden layer to the end. So there's a lot of weights, and it got a 96% accuracy. So here are the first 25 digits and how well it did. And you can see it got the 9 right now, but it still got this one wrong. Okay? Which is understandable. And this is the first 25 that it got wrong, actually. So again, you know, some of these are kind of understandable, but some, I don't know, seems like a 0 to me. You know, some are, you know, they're okay. All right. So now what we're going to do, so that was a general feed-forward, fully connected neural network. And so now I'll hand it back to Aaliyah, and we're going to do it a third way, something called a convolutional neural network, which is a particular style that's very good with images. Okay?
All right. Thanks. Okay. So what's the problem with using a fully connected neural network for image recognition? So the problem is that in this example, so we had, remember, 28 by 28 pixel images. We lined up all the pixels in a vector. And then we added a hidden layer where each of the hidden nodes is connected to every one of the 784 input pixels. And this was the architecture we used to get the results. Now, it's doing fine in this case, but when you're connecting every one of your hidden nodes to every one of the inputs, the number of parameters increases very quickly. So for example, for a 28 by 28 image, i.e. 784 input nodes, if I add 2 layers, 2 hidden layers, each one of them having, say, 500 nodes or something, ultimately, I would have over 500,000 parameters that I need to train. That's not good. That's way too many. And the other thing is that when we lined up the pixels in a vector instead of the original array, we basically ignored most of the spatial information included in that image. Like, we know that pixels that are close to each other are more likely to be related and informative than the pixel in the beginning of the image and the very last pixel in the image. And we're not giving the network this head start of this knowledge. It's having to rediscover that from scratch. So that's very inefficient. So what we do to fix this is we use a convolutional neural network, which are really, really good for image applications. So the idea here is that instead of connecting every hidden node to every pixel of the image and making it responsible for understanding the whole image, we let every hidden node focus on only one portion of the image. So it's only responsible for understanding its own designated region. So that dramatically decreases the number of parameters you have to learn. And then the other thing we can think of is, say, this node is responsible for checking if I have an eye in this portion of the image. Okay, so it has certain weights that are optimized to detect eyes. Now, say this hidden node is also trying to detect an eye in this portion of the image. Do you feel like they should have different weights? Not really, right? Because an eye is an eye wherever it appears. So a hidden node that's responsible for detecting an eye should have the same weights as another hidden node also detecting an eye. And that also dramatically reduces the parameters that you have to learn. So for example, this is a 7 as input, and see, we're giving the input as an array, not a vector. So we're not losing any spatial information. In the hidden layer, this node is responsible, say, for finding, I don't know, horizontal edges in this portion of the image. And the second node is also looking for horizontal edges with the same weights in this portion of the image, and so on. Now, all of these nodes are looking for the same thing, the horizontal edge, just in different regions. We call them a feature map. So a feature map is just a set of nodes looking for one feature everywhere in the image. Now, we can have another feature map for, say, vertical edges, another feature map for circles, and so on. And then we combine their intermediate predictions, I guess, combine all of these, and I'm abstracting so much here, to say, oh, this is a 7. Now, one thing I want to emphasize is that we actually don't tell the feature map what feature to look for. So I would not tell this hidden layer to look for a horizontal edge or a vertical edge. The optimal features to look for emerge naturally in the training process. So all you specify for the network is how many layers, how many nodes. And then as you train it on loads and loads of data, by itself it discovers that, oh, it's very informative if I look for this kind of edge here. So a convolutional neural network overall would consist of an input layer, a bunch of convolutional layers like the one I showed you here, and then something called a pooling layer, which really all it does is just summarizes the results of the previous layers, just shrinks the dimensions a bit so things don't blow up. And we stack as many of these as we need, and then we reach the output. Now, it's hard to really understand what exactly every node is doing, but overall, this tends to be what's happening. You start with an image that has a lot of spatial information, a grid of pixels. And as it goes through the network, in the first layers, you're looking for simple features like edges and circles and tiny things. And then as we move forward in the network, the features we're looking for get more and more abstract, until at the very end of the network, you're just looking for abstract concepts like, is there a cat, is there a wheel? And there is very little pixel detail information present. And this is basically how the brain works, more or less. So in the eye, in the cortex, you have these cells that each one of them specializes in one portion of the image you're perceiving and of its receptive field. And then they do very basic processing. The first layers are just looking for very simple edges. And then they pass on their transformed images to the next layer and next layer. And by the time this information reaches, your prefrontal cortex or wherever you're making decisions in the brain, what you have is just concepts. So now let's see if a CNN is actually doing better on the digit problem.
I'll try not to hit the down arrow. Okay, so CNN, so a couple things about that. So one is, just to reflect on what Aaliyah said, there's an intermediateness to the way you think. Like when you see this, you think of it as an 8. But when you were a baby, you might say, well, if you see a circle on top of a circle, that's an 8. So you're kind of seeing the two circles, and then you're saying, okay, that's an 8. Or if I had a picture of this room, I'd say, oh, there's a lot of people, there's chairs, they're all looking the same way, must be a classroom. There's kind of intermediate steps that you take in thinking. So that's the idea behind a neural network itself. And these middle layers are somewhat magical, but a CNN focuses these hidden cells on a little part of the image, essentially. So you're kind of helping the network in its architecture look at images, essentially. Okay, how well do you think this one worked? 98, let's see. 99.36. Yeah, so this did great. So here are the first 25 digits that I got right, and you can see it now got this one right somehow. That's a 5. Must be mistrained. And then here are the next 150 digits, and I got all these right. So it didn't get everything right, but it takes a while for this thing to sort of end up with one wrong. So here was our summary. So 92% using the techniques of last time, the linear separation. A fully connected neural network gets 96, and then a CNN gets 98. So it's really, impressive how, and it's the same data set, and even if you imagine sort of the code that Aaliyah is talking about to sort of do this stuff, it's actually not that complicated. It's really a breakthrough in approach and a lot of data. Okay, so I'll close with a couple comments about it. So one is, we're in a boom of AI, right? It's a total buzzword and stuff like that. And you could wonder, when did this start? And I think it essentially started in 2012, and I'll describe why. So there's this yearly competition and database called ImageNet. And the classic problem was always, why can't we teach a computer to understand a cat versus a dog? Babies can do this. Humans can do this very easily, but computers can't do it. That was sort of the age-old problem. This is a version of that, where you have all these images, and you have to identify what's in the image. And so they had this annual competition that started actually in 2005, but I couldn't find the data, where these teams would compete. And in 2010, for instance, they were 28% inaccurate. So not so good, at guessing what's in the picture. And it was like that in the past. So always 30% or something like that inaccurate. And then it all of a sudden dropped to 16%. And then it dropped again to 10. And then it dropped again to 6. And so we had these major advances over this 3-year period to eventually, by 2015, we were better than humans. Okay? So this is when all the excitement began. And this is actually when CNN started to get used, and some of this architecture that we talked about today started to get discovered, is around then. So this is when we sort of cracked the image recognition nut. Okay, and then let me, there's one other topic if we had time. So what are the recent breakthroughs? Because some of you might recognize some of these algorithms from a long time ago, if you were around a long time ago. So the recent breakthroughs are really data. So let's just say images. Now we have labeled images. 50 years ago, we didn't have all these digitized images that said, hey, this is a picture of me in the Eiffel Tower. Now we have images galore on Google and Facebook and everywhere else that can be labeled. The second thing is, when you're training millions of weights, if you imagine what these programs do, they do a lot of matrix math. And so we have CPUs that are built to do matrix math now. And so if you have and that's all they do, essentially. So if you have the right CPU, matrix math can also be heavily parallelized, work on these different parts of the matrix and summarize. So there's CPUs that are very good at deep learning, and so it's conceivable to train millions of weights in a half hour kind of thing. And then new algorithms like the CNN approach. There's one, maybe we'll have a machine learning 301 someday, backpropagation, transfer learning. There's some approaches that we've come up with. Okay, so to summarize what we covered today is classification is really the type of machine learning we've talked about, which is you have features and you're trying to figure out a function that determines the class. Linear separation was last time, and then these two neural networks we did this time. And I'll just show you I like doing topical news. This was from my Twitter feed this morning. And I sort of like this thing. It says, this guy, whoever he is, Amazon learns from every click. And healthcare only analyze a % of data over a long period of time. Like, we certainly don't learn from every patient encounter, every lab test, everything that happens to a patient. We do very little learning in healthcare if you really think about what happens, other than personal learning. Like if you're a doctor or a surgeon, or you try something and it seems to work, then you learn. Or we do clinical trials. There's that kind of learning. But this kind of learning that Amazon does, where every click, every purchase, every kind of interaction, these kind of companies are learning from, collecting that data and learning from it. So there's an enormous potential in healthcare to sort of apply this and make the whole system better. And you could argue we haven't even scratched the surface, really. All right, so that's it. Any final questions, comments? Yes?